Now, many investigators like to consider designs other than randomized designs. There's often concern that randomization may not be acceptable to the people that you're going to try to recruit for your study. Or sometimes people think, well, randomized designs are just too complicated and too hard, and they're too big and too expensive. And if I do something other than a randomized design, it will be less expensive, easier, simpler. So I want to talk about some of the alternatives that are commonly offered, commonly discussed, and see how they compare to the designs that we've already talked about. I'm going to talk about multiple baseline. I'll talk about time series. I'll talk about quasi-experiments, and I'll talk about regression discontinuity. There's a paper now, 14 years old, published in 2010, that compares these to group randomized trials for power and cost. And you may find that paper interesting. Shadish, Cook, and Campbell also discuss all of these designs in their 2002 textbook, which is still quite solid, even though it's now 20 years old. We'll start with multiple baseline designs. Here, it's like a group randomized trial, except we don't have randomization. In fact, it's a lot like a step wedge design, except we don't have randomization. And it's usually a very small number of groups rather than a larger number as we usually have in a step wedge. But the feature that's similar to step wedge is that we're introducing the intervention into our groups one at a time and on a staggered schedule. That's exactly what we do in the step wedge design. We're collecting data in all groups at each entry point. We're very often this approach will be used with just 3 or 4 groups, so it's small. And you look at the data and hope that the changes that you see in the outcome are consistent with the way that you've introduced the intervention. There's not a good statistical analysis for this design. The interpretation of the data is based on logic and what it looks like, what the pictures look like, rather than statistical analysis. But if you get the right kind of pattern, it can be fairly convincing. So this is a pretend example, a hypothetical example. This is from a paper by Hawkins et al. 2007. They were arguing for the multiple baseline design. And this is 4 communities. We've collected data every month for at least 4 months in community A before we introduce the intervention, and we keep collecting data for many months after the intervention is in place. In community B, we collect more baseline data for a longer period of time, then introduce the intervention and keep collecting data. Same thing with community C, and finally we get to community D, where we've had baseline data for a long time, introduce the intervention, and then only have limited observations under intervention. This is a terrific pattern. If you showed me these data from your study, I would be substantially persuaded that the intervention is the cause for the change that you're seeing. The intervention occurs only, or the change occurs only when the intervention is introduced. It occurs rapidly, and the effect is persistent. So if you've got that sort of pattern in your data, great. You can publish it and be pretty comfortable. The catch is that this design is not very good if the intervention effects are expected to be small or take some time to develop or fade over time after you observe them. And it's a very bad choice if the intervention effect is expected to be inconsistent across groups. You'll see noise rather than this nice clean pattern. So the evaluation relies on logic, not on statistics. And I discourage people from this approach if they think the effects are going to be small or gradual, or if they think they might vary appreciably among the groups that they're going to use. What about a time series design? It's a great design for looking at the effect of an intervention in a single group. It requires repeated and reliable methods or measurements. Very often you'll need as many as 50 measurements before the intervention is introduced, and perhaps another 50 after the intervention is introduced. So it works very well if you've got archival data where the data are being collected routinely, administratively, and all you have to do is grab them out of a database and look at them. So we see this kind of design applied, for example, to studies looking at the effect of changing the age at which individuals can get a driver's license, or the age at which individuals can buy alcohol. So it works well where we can access archival data. We can use standard methods to look at change within a single group. But if we've only got the one group, we don't have a comparison of any kind. So if we do have another group where we're not introducing the intervention, we can compare the diagrams, the figures for the two groups, but it's really, we don't have a statistical approach to look at the difference between the groups because we've only got one group in each arm. So we don't have any degrees of freedom. Even so, if you set things up well, so you've got lots of observations before and after. Even better if you've got multiple states or counties or groups where the intervention is being delivered. If you're collecting data on another outcome that is normally correlated with the one that's of interest, but isn't expected to be influenced by the intervention, and you can show that it didn't change when the intervention was introduced, that can be very helpful. This is the kind of data that we often see. So in 2002, 3, and 4, we've been collecting data on sexually transmitted disease infection rates. Each year, the trend is going up. There's bounce from month to month, as you might expect. And the intervention is introduced at the beginning of 2005, and the angle of the line didn't change, the slope didn't change, but the intercept dropped. So the line in the gray shading is lower than we had expected it to be if things had just continued. And that's evidence of an intervention effect. And the analytic methods available would tell us if that difference is statistically significant within this one group that we're looking at. Again, there's no comparison here. If we had a comparison line, there's no statistical analysis to compare the intervention and control series unless we have multiple groups in each arm. And that is uncommon. So a lot of the interpretation relies on logic, but it can be useful. What about quasi-experiments? People come to me all the time and say, David, I want to use a quasi-experiment instead of one of these large, expensive group randomized trials. And my answer generally is, good luck. And you're probably going to have as large a study and as expensive a study at the end of the day as if you'd had a randomized study, if you do it well. If you're not going to do it well, then yeah, you can get away with something that's smaller and less expensive, but it's not going to be done well, and you're not going to get as much out of it. So quasi-experiments have all the features of experiments except randomization. To me, that's a disadvantage. Causal inference requires elimination of plausible alternative explanations, where if I have randomization, I can rely on randomization for causal inference. If groups are assigned to study arms and members are observed, the data analytic methods and the sample size methods are identical to a parallel group randomized trial. So you haven't saved yourself anything. Certainly, I would encourage the use of a quasi-experiment if randomization is just not possible. It can give you experience with things. It can provide evidence of treatment effects if the study is done well. But I would argue that a well-designed, well-analyzed quasi-experiment is usually harder to do, more expensive than a well-designed and well-analyzed parallel group randomized trial. What about regression discontinuity designs? Will Shadish introduced me to regression discontinuity designs when he and I were on the faculty together in Memphis around 2000, 1999 perhaps. And I'm quite fond of a regression discontinuity design. I'm a big fan. It as an example on the surface of getting your cake and getting to eat it too, there's always a price, and there is. But the point of the way that the regression discontinuity design works, individuals are assigned to study arms based on a quantitative score of some sort, often reflecting need. So you give the people who need the intervention the most the intervention, and the people that don't need the intervention as much provide the control observations. That sounds terrific. We ought to be able to do that every time. How in the world can you get a valid intervention effect estimate out of that kind of study? Well, it turns out you can if you do it right. The analysis models the relationship between the assignment variable and the outcome, and the difference in intercepts at the cutoff, at the breakpoint, is the estimate of the intervention effect. And there have been a number of papers on regression discontinuity in public health and medicine, and I've listed some of them here. Let's look at an example. The upper panel is an example where there's no treatment effect. So this is a regression discontinuity design, but no treatment effect. Everybody below who got a score of 50 and under was assigned to treatment. Everybody that got a score above 50 was assigned to control. And if you look at the slope, it is the same in treatment and control, and there is no separation at the cutoff. The line didn't shift up or down, the slope didn't change, and so we conclude, well, the intervention didn't work. No evidence of intervention. The relationship between the assignment variable and the outcome is the same in treatment and control. In the lower panel, we have an effective treatment. So we see the pattern in the control arm is just as it was in the upper panel, but the pattern in the treatment arm is different. The whole line is shifted up. Everybody did better. So this is one of several different kinds of treatment effects that you can see in regression discontinuity designs. The intervention effect is estimated as the difference at the cut point between the two lines. Sometimes you'll see this kind of effect where it's a difference in intercepts. Sometimes you'll see a difference in slopes where maybe it looks more like the upper panel, but at the cut point, the line increased in slope or decreased in slope. Sometimes you'll have a mix of those two things. So you can have different patterns, but the idea is that the pattern looks different on one side of the cut point than it does on the other. If you model the relationship between the assignment variable and the outcome correctly, then the assignment to study arms is completely, fully explained by the assignment variable. And you can draw a causal inference from this design. And that's from no less of an expert than Don Rubin, who published a paper in 1977 on regression discontinuity designs. Most of us know him from his work on multiple imputation. Regression discontinuity designs don't have randomization, but they can give you as strong evidence for causal inference as you can get from an RCT or any other kind of a randomized trial. So they're terrific in terms of evidence for causal inference. The price, and I said there's always a price, they are less efficient than an RCT or a group randomized trial. They often require twice as many participants. So if you're in a situation where the participant cost is not so bad, you might be able to consider this. Most of the time when you read about regression discontinuity designs, the assignment of participants is at the individual level. So individuals who score above or below a cut point are assigned to study arms. We've adapted the regression discontinuity design to be used in the context of a group randomized trial. Mike Pennell did that in a paper published in 2011. And the Research Methods Resources website includes now a section on group or cluster-based regression discontinuity designs, including the sample size calculator that's based on the methods that Mike Pennell described in that paper. So you can find that if you go to the website and that kind of design is of interest to you. So in summary, in terms of alternative designs, there are a number of alternatives that have been proposed. Step wedge designs we talked about early, we've talked about as we've gone on. I don't think they're as good as a parallel group randomized trial. But if you can't use the parallel group randomized trial, a step wedge design can still be useful. The multiple baseline design has lots of apparent advantages, but when you look closely, the disadvantages are substantial. Time series designs, often the only kind of evaluation that you can do when you've got policy level interventions. So you can do pretty well with those if you've got plenty of observations, especially if you've got data on outcomes normally related to your outcome of interest, but unaffected by the intervention. Quasi-experimental designs, if you can't randomize, a quasi-experiment can be used. If you do it well, it's going to be virtually as large and expensive and complicated as a parallel group randomized trial. And if you're assigning groups and observing members of those groups, the analytic methods and sample size methods are going to be the same as for a parallel group randomized trial. So no real advantage. Regression discontinuity designs, I'm in favor. They're strong, good basis for causal inference. The price is you need a larger study, often twice as many participants. The multiple baseline and time series rely more on logic than statistics. The quasi-experiment and regression discontinuity certainly rely on statistics, but you may need a study just as big or even larger than a parallel group randomized trial. And I believe that wraps things up for today. If I click forward, I get a black screen, so I'm definitely done.